This is a presentation about a new general rendering algorithm dealing with difficult light paths. We focus on rendering scenes with difficult light paths, such as the one that contain multiple glossy materials and possibly combining with other effects like motion blur. These light paths are difficult to render because their contribution regions are usually sparse and narrow. It can make your image noisy if you don't have enough samples. To illustrate why this is difficult and how we plan to deal with it, let's look at this scene where there is a highly glossy gold brine lit by a distant point light. Let's focus on the light path in the red region. Let me zoom in to have a better view. Here's a light path connecting from the light to the eye. It has high contribution because the glossy material on vertex 1 above is reflecting many photons toward vertex 2 below. Now, we want to look at the nearby light paths. The nearby light paths can have very different contribution compared to the original light path. In general, this is due to a variety of factors, such as the curvature of the surfaces, the material properties, and light positions. For example, if we move vertex 1 to another position, it is very likely that the new light path will go off the peak of the glossy reflection and does not contribute to the image. And the same thing happens if you try to move vertex 2. So, let's try to visualize the contribution function by moving these two vertices on the corresponding directions. And we get the plot on the right. Every point on the horizontal coordinates correspond to a light path with different offsets in blue and red directions. We record the light path contribution on the axis pointing up, and we draw this 3D landscape of path contribution. For example, the yellow sample on the center of the plot corresponds to the original light path. Red and blue sample represent the light path with moved vertex 1 and vertex 2 correspondingly. What you can observe here is that while the contribution is continuous, it is both sparse and anisotropic. By anisotropic, I mean the function usually has different degree of smoothness at different directions. The sparsity and anisotropy are causing some troubles to us. For example, if you only move one of the vertices, it is very likely that your new path will have zero contribution, just like the red and blue samples. Traditional multicolor sampling is not very efficient on this narrow function. Notice that we don't actually know the whole contribution function. What we can do here is to shoot point sample on it. Unfortunately, many of the samples do not contribute to the image at all, and this is the source of the noise. There is a more advanced rendering algorithm called Metropolis light transport. The idea is to maintain a Markov chain of light path samples to stay in the high contribution region. Given the yellow sample in the center, we try to generate sample n+1 around the yellow sample, and then we try to generate n+2 around n+1, and so on. To generate sample n+1, we draw a proposal from a proposal distribution. The proposals are then probabilistically accepted to become the next state. However, the choice of proposal distribution is crucial. It needs to be similar to the contribution function, at least locally, because the probability of rejecting the proposals depends on their contributions. Low contribution proposals will end up being rejected. The fact that the contribution function is anisotropic makes this difficult, because you can't just blindly move the vertices of the light path, or you'll end up being rejected. Our method builds on Metropolis light transport algorithm, and we focus on building an efficient local sampling strategy, so that the proposals stay in high contribution regions. The goal is to generate new proposals so that they adapt to the anisotropy of the integrand. In other words, we want the proposals has high probability to land on high contribution region, so that we can explore the contribution function while reducing the probability of rejection. There are some previous works on efficient local sampling for Metropolis light transport, specialized for microphased BRDFs. They utilize constraints based on the mirror direction to sample the light paths. Our method is different in two aspects. First, we aim for a fully general approach. For example, our method can be easily extended to time dimension and detect the anisotropy of a moving multi-bounce glossy light path. Second, we want to characterize the anisotropy of all directions at once, and these specialized methods need to sample from some dimension first, then resolve the rest using the constraints. So, let me restate our goal. We build our Metropolis light transport algorithm and try to come up with a proposal distribution that adapts to the anisotropy of the integrand. We want the proposal to have higher probability to land on high contribution region. We also want our method to be fully general so that we can use it to render any effects. The goal boils down to two challenges. First, we need to characterize the anisotropy of the contribution. We use the Hessian as well as the gradient of the sample. This gives us a quadratic approximation around the current sample. Next, we need to sample from this quadratic approximation so that our proposal has higher chance to land on high contribution region. This may be more difficult than it sounds because quadratics grow to infinity and do not define distributions. To overcome this, we borrow ideas from Hamiltonian dynamics. But before I talk about Hamiltonian dynamics, let me talk about the characterization part first. Specifically, why we are using the Hessian to characterize the anisotropy, and how do we compute it. The gradient of the function points to the strongest increased direction. It tells us where to go if we are seeking for higher contribution. However, it only gives us a single directional information. In contrast, Hessian gives us information on all directions. It tells us what happens to the function if we move two of the coordinates simultaneously. In other words, it gives us a correlation between sampling coordinates. This is a very important information for us because we want to characterize the anisotropy in all directions at once. To compute gradients and Hessians, we use automatic differentiation. It's a metaprogramming approach that applies chain rules to your program automatically so that you don't need to hand-derive the derivatives. Given your program that you want to differentiate, in practice, you replace the floating point type to a special data type. The special data type records the function so that the function becomes sequences of operations. It then applies chain rules to the sequences to compute the derivatives of the function. To apply automatic differentiation to our renderer, we have to implement the whole path contribution function with that special data type. Therefore, the derivatives take account for the full path contribution, including normal, BRDF, and an emission profile of the light source. The derivatives are taken with respect to path vertex coordinates that parameterizes the light path. To have more intuition about what gradients and Hessian gives us, let's look at the original contribution function here. Remember that we only know the contribution at the current sample. However, the gradient and Hessian of the current sample gives us a quadratic approximation about its neighborhood. The quadratic approximation looks like this. It's an approximation, so it's different, but you can see that when I'm flipping between the slides, it captures the local shapes of the contribution function. So now, instead of one point, we have the whole quadratic function to reason about, and that's a lot of information. The problem now is how to utilize this information. To recap, now we have a quadratic approximation around the sample, computed by automatic differentiation. The quadratic approximation characterizes the anisotropy of the function. We want to sample from the quadratic so that the proposal has high probability to land on high contribution region. As I said, this is not that trivial because the quadratics can grow to infinity and do not define the distribution. We cannot just apply something like inversion sampling to the quadratics and hope that we can get the proposal. Therefore, we borrow ideas from Hamiltonian Monte Carlo. The goal is to attract samples to high contribution regions. The idea is to flip the landscape so that high contribution regions are not at low ground. We then simulate physics on the landscape so that gravity will attract samples to low ground. which represent high contribution regions now. Let me be a little bit more specific. Now we have flipped the contribution landscape. Imagine we put the particle at the current sample location. We give the particle a random initial velocity, so the particle will roll on the landscape. Because of gravity, the particle will be pulled to low ground. And because we have flipped the contribution landscape, low ground now represents high contribution area. We record the final position of the particle after some fixed time, and the final position is our new proposal. Unfortunately, it is not feasible for us to apply traditional Hamiltonian Monte Carlo directly. In its original form, Hamiltonian Monte Carlo requires expensive numerical simulation to do the physics. In our case, it means that we have to do all the ray tracing, shading, and derivatives computation along the trajectory. Fortunately, in this particular case of quadratic surfaces, and if the initial random velocity is Gaussian, we have a closed-form solution. To demonstrate the closed-form solution, recall that the particle is given a randomized initial velocity. In our case, we assume it is Gaussian distributed. If you give the particle a different velocity, it ends up at different locations. And if you try this many times, you can observe that the end position of these particles form a Gaussian distribution. It turns out that Hamiltonian dynamics is a linear operation on the Gaussian velocity variable. So essentially, Hamiltonian dynamics transform the velocity Gaussian to another Gaussian representing the final positions. It means that we can do all the Hamiltonian Monte Carlo business to sample the quadratic surface by sampling from an anisotropic Gaussian whose mean and covariance metrics can be derived from the quadratic surface and Gaussian initial velocity. To recap, given the current sample, we use its Hessian as well as gradient to characterize the anisotropy of the contribution function. This gives us a quadratic approximation around the current sample. We want to sample from the quadratic approximation. However, the quadratic does not define the distribution. So, we simulate Hamiltonian dynamics to sample from the quadratics. This results in a closed-form Gaussian, so we can just sample from this Gaussian. Recall that we built our method on Metropolis light transport, and we are generating the Markov chain. So the full algorithm is, given the current sample, we compute its gradient and Hessian. We then compute an anisotropic Gaussian based on Hamiltonian Monte Carlo and the gradient and Hessian. We draw a proposal from the Gaussian and probabilistically accept it. If it's accepted, then current sample becomes the accepted proposal. And we repeat the process. Let's look at the result. Here's our test scene, rendered by our method in 10 minutes. The scene contains many glossy materials. For example, the metal ring is causing some caustics on the right wall, and the glossy bathtub is reflecting light from the whole room. I want you to focus on two regions where there are some highly curved glossy surfaces involved. Here is the equal time comparison of one of the insets between the methods. We compare with three other Metropolis light transport algorithms. The highly curved metal ring is troublesome for all the other methods. Multiplex Metropolis light transport, as known as MMLT, uses isotropic mutation and cannot handle anisotropic integrand very well. Manifold exploration and heft vector space light transport, as known as MEMLT and HSLD, which are the specialized methods I mentioned when I was talking about previous works, cannot explore the contribution function efficiently because they need to sample some coordinates first, then resolve the rest using some constraints. And it is possible that during the first pass, they jump into some space where it is impossible to specify the constraints. Our method is pretty good at resolving the correlation between coordinates, using second derivatives, even with the highly curved surfaces involved. Here's another example where there are some fast-changing normals on the edges. This is pretty troublesome for Metropolis light transport algorithms because you need to sample on the edges in order to keep staying on high contribution region. Again, we can handle this pretty well. This is another scene showing the generality of our method. Specifically, our method is able to resolve the correlation between the time dimension and the path space, thanks to automatic differentiation. Here's a closer look. We do not show the result of HSLT here because their implementation does not support motion blur. MMLT sometimes trapped in a very narrow region and produced some correlated noise. Manifold exploration produces ghosting artifacts because they do not move in time dimension. Again, our method can resolve the correlation between time and path space and did it quite well in this case. To conclude, we proposed an algorithm where the goal is to generate good proposals for Metropolis light transport. We use Hessian computed by automatic differentiation to characterize the anisotropy of the integrand. We then use Hamiltonian Monte Carlo to sample from the quadratic approximation. This results in a closed-form Gaussian, so we can just sample from this Gaussian. Our method is general thanks to automatic differentiation. For example, it can be easily extended to sample time dimension. Thanks for listening.